댓글도 안 줬어. 가디건 벗었나 봐.
안에 입고는 있어요.
지금 저건데? 난방인데?
안에.
단축 골랐구나. 너무 섭하고 추웠어.
Okay, reporter, please begin whenever you're ready.
얘좀 비교해볼까? 할 때만 하라 이거지. 이게 물병이에요? 무슨 물병? 무슨 뭐를?
일단
I'll start the presentation. Good morning, ladies and gentlemen. My name is Miruki, representing Team Format from Hana Academy Seoul, and I'm the presenter of the problem number 17, water bottle. Here's the problem statement. When you launch a partially filled water bottle, it performs a somersault before landing on a horizontal surface in a stable and upright position. So it was to investigate the parameters that affect in the successful flip. So I was to make the successful flip and investigate the parameters. First, the observation. I actually made an example of handmade flip with this dyed water. And as you see, it flips around and it lands in exact upright position right on the floor. So I have to investigate the parameters that affect the motion. And before we actually start in modeling this whole water bottle flip, I have mentioned that I could not come up with any mathematical model to explain this in actual 3D coordinate. So I actually reduced it to 2D analysis to have a mathematical model for this whole process. So here's the flow chart. I first have the qualitative approach, and I divide the whole process into two parts, which are the flipping process and the landing process. And I have quantitative modeling of my model, including the angular momentum change of the bottle flipping. And I compare the maximum angle with critical angle, and this critical angle actually varies from the initial height of the water block. So I have this modeling. And in the experiment, I had an experiment of the flipping process to validify the whole modeling that I did. And then I actually measured the maximum critical angle dependent on the height and proved my approximation. And then I'll move on to the final results to show which conditions make this successful flip. So here's the theoretical approach. The first part is the flipping process of the bottle. For the water bottle, for the water block inside the bottle, I named it liquid body. So it actually acts like a liquid in dynamics, but in terms of interaction with the bottle, it actually exerts force, or it has collision with the water bottle. So I named it liquid body. So here are four processes of the whole water bottle flipping process. In the first process, we start the launch and we exert the initial kinetic energy. And actually, during the first stage, the center of mass and the rate of distribution actually keeps pretty same at this place. So the angular velocity is at constant. But at the second stage, as the water goes almost 180 degrees, and the water actually starts to fall vertically. And after the stage 2, the water bottle actually collides with the bottle, and it decreases the bottle's angular velocity. And at the last stage, the water fills the whole space and keeps rotating at a final angular velocity. So at the first stage, as you see in the video, the water's radius distribution is pretty constant. So the center of mass is at its place, and so it keeps its initial angular velocity. But then, when it is rotated almost vertically upside down, the water bottle actually starts to fall, and it collides with the water bottle itself, decreasing its angular momentum. And at the third stage, the water actually fills the whole water bottle space, and it rotates with its final angular velocity and angular momentum. And now moving on to the landing process. I compare the kinetic energy and the gravitational, the work done by the gravitational torque. And then this inequality is led by the critical conditions. So first, as the bottle lands on the floor, there is obviously the initial kinetic energy gained by the rotational energy and energy from initial velocity. But then there's the work done by the gravitational torque. And the bottle flips a little bit more after it lands. And when the work done by the gravitational torque is equal to the initial kinetic energy, it stops and makes the maximum angle with the ground. So then, for the successful flip, this maximum angle has to be under a certain critical angle above which the water bottle never will be never will be able to stand in the upright position. So now I'll move on to the quantitative model analysis and actually derive some equations explaining these phenomena. So first, when you throw this water bottle in initial angular velocity omega I, the initial angular momentum can be calculated simply, and I1 and I2 represents the momentum inertia of the water block and the water bottle, respectively. Now, when it is turned upside down, the water actually slides a little and forms a triangular shape. This is done by the observation, and the displacement of the flow along the wall can be expressed like this since the time interval is very short, so we can consider that as a free fall situation. And since during the waterfall, the bottle keeps rotating, so we balance the length and get the rotating time until the collision. So for their rotating time, the whole variables here can be expressed using the rotating time t and some initial conditions like omega I. So then the momentum change right here, mRu sine alpha, can be expressed with those initial terms, and the Li was introduced before. So we get the final angular momentum Lf. So from that, we gain the omega f, the final angular velocity, and also integrating with time, we get the final angle. So from the initial conditions, we get the final conditions when it lands on the floor. So now moving on to the landing process. For successful flip, there should be an angle above which it fails to success in a flip. So this angle can be expressed like this. It's dependent on m and those mass and height stuff, and also the radius of the bottom. So when it lands on the floor, the omega changes a little, and the initial kinetic energy can be expressed like this. So it is dependent absolutely on the initial conditions of the water bottle flip. So then, during the motion, this angular acceleration can be expressed using the torque, and the torque term includes obviously the theta, the angle it makes with the ground. So this differential equation can be gained, and the initial condition for the differential equation is gained from that flipping process we did, and using the theta f and the omega f. So since we know the theta dependent on the time t, we get the total work done by the gravitational torque. And when this total work done by the gravitational torque is equal to the initial kinetic energy, we know we can obtain the time that it rotated. So putting that time back in and integrating twice about the angular acceleration, we get the maximum angle it makes with the ground, and it is expressed like this. So you see this maximum angle is expressed with various initial condition terms like theta here and theta here. So setting this maximum angle to be under the critical angle theta c, we know that the bottle will make a successful flip. So this is the main condition we have focused on. And then about the critical angle, what would make critical angle at its maximum? We concluded that the initial water height would be an important parameter. So assuming that there's a linear relationship between the mass and the height because the basal area is constant or along the z-axis, the tangent theta can be expressed like this, and this is how the graph looks like. So I'll show that in the experiment. So the initial height can be expressed like this. I derived this myself. So the alpha is the ratio between the mass of the bottle per unit length, to the mass of the liquid per length. So I decided to call this the ideal height. And I'll show you how these all simplification and modeling actually works with exact experimental setup. So this is basically my experimental setup. To modify this, there's a rod here and there's a stand here. And so here the control variables are the initial height of the mass and the initial height of the water bottle and the contact point that the rod hits the water bottle. And for the bottle parameters, I use 3 types of bottles with different volumes and mass. So first, I'll show you how the flipping process happens. So like you can see in the video, but there's a sudden decrease in angular velocity, like you saw in the observation part. So this is how the graph looks like. This graph, the x-axis is initial angular velocity, and the y-axis means the final omega, the final angular velocity. So this line represents that the initial velocity and the final velocity is the same, but the actual line, the theoretical line, places a little beyond, a little under the line, which means that the final angular velocity is less than initial angular velocity. So this verifies my model for the flipping process. And next, I set for maximum critical angle. So I check the critical angle dependent on height. So I vary the height. So for the first bottle, this black line represents the relationship between the height or the volume and the critical angle. So it seems to match pretty well. You can see that there is a critical angle right here. Also for the second bottle, the third bottle, obviously. So, and in the second bottle especially, the dots seem to lie a little behind the line, and that's because the mass distribution is not really homogeneous, but is pretty concentrated on the bottom top part. So I'll introduce my last graph. This x-axis represents the initial omega, and this represents the initial velocity, the x-axis. And I set the y velocity to be constant in this experiment because I thought it's the less relevant parameter and it only determines the time. So this blue dots means that when the initial angular velocity and the initial linear velocity is set, it succeeds to stand in a vertical position, and if the conditions lie on the red dot, it fails to succeed. So I compared it with this experimental values, and this green dot means it is most successful, and the orange dot was a little bit less than the green line, but it was still successful, and this seems to match pretty well with the theoretical expectations. Also for the second bottle, it seems to match pretty well. And for the third bottle, if you see this, the number of the blue dots in this region actually seem to increase, and this is because the third bottle had the largest radius of the bottom area, so it was most probable, and this critical angle was the largest. So this experimental results seem to match pretty well as well. So for the conclusion, the whole problem was about investigating parameters that would result in a successful flip. So what makes the best water bottle for me? First, the amount of water and the height of the water bottle. Second, the shape aspects of the bottle, such as the mass distribution or the radius of the bottom area. And the initial dynamics of the fluid, obviously, such as the velocity, initial velocity or the initial angular velocity of the water volume. And last, this is not a physical parameter, but the flipper skill might also be a value, but this is just a joke, sorry about it. So that's all for my presentation. I just show you how you can make a successful flip. Follow this, be a successful flipper. Thank you.
Okay. Opponent, please feel free to ask questions to the reporter.
Thank you, sir. And since the lack of time, I have about 12 questions to ask to you. So would you, can I request for you for the short answers?
Okay, keep it short.
Yes, thank you. Did you take into account the bottle function? Like, it means the properties like size and shape when the calculation?
What do you mean by size and shape? I consider size and shapes.
But I mean the shape of the bottle. So it can be like this kind of shape or this kind of shape.
No, I didn't take that into account.
Okay, sir. So can you explain why the rebounding occurs when rebounding occurs or rebounding not occurs?
Given that initial velocity in vertical, given the initial vertical velocities the bouncing didn't really happen usually.
Yes, sir. So do you believe the critical angle is constant?
It's constant when the initial conditions are given.
It is constant with the initial conditions given. Okay, I'm going to deal with it later. And I'm going to ask you that, did you take into account the deformation effect of the bottle when it clashes with the ground?
No, I didn't take that into account.
This question is for checking the parameter control. So it seems you have used the same bottle, like three types of bottle, during your experiments. And did you use the same kind of bottle?
Oh yes, I used 3 types of bottle.
Excuse me, sir?
I used 3 types of bottle, as you see.
3 types of bottle, and then 3 types of bottle for each of the 3 types of bottle. One for each of the 3 types of the bottle. Can you understand my question?
Not really.
Oh, sorry, sir.
Let's talk about that
later. Okay. So, did you take account the friction between the floor and the bottle when it touches to the ground?
No, I didn't really take that into account. I don't think that's an important parameter.
Okay, sir. So, did you consider the collision between the bottle and the floor with the collision of the rigid
total
bottle?
effect between the floor and the bottle.
Okay, you considered?
No, I did not.
I did not consider. Okay, sir. So, do you think the kinetic energy is conserved in your total theoretical model?
It is conserved when you see the whole system as well, but if you only see it at the bottom, it's not conserved.
Okay,
Okay, thank you.
call off you guys here. Opponent, please take 3 minutes or 2 minutes to prepare.
아니 거기까지 또 내가 대전역이 좀 멀어. 근데 SRT는 대전역밖에 없어가지고. 50분, 55분. 아니 서울역까지
Okay, opponent, please take the floor and start your discussion with the reporter when you're ready.
Yes, sir. So, I'm Mitchell Park, who is the team captain of the team Magnets, and today I'm going to present about the opponent's speech relating to the number 17 problem, water bottle. So the problem is just stated like this, and then I have considered the somersault is also the key point of this problem, different with the presenter team. And this is the short presentation overview. So they have stated the problem, and they suggested the rigid body model, and they have suggested the constant, critical angle, and they have calculated with their model about the critical angle. And also they showed some experiments that can support their data, their theoretical model. And also they have suggested some other kind of conclusion related to the maximum critical angle. And here are some points of the strengths and weaknesses related to his speech. The kind of strengths is he has the quantitative model and all this his model are kind of his strength in his theory. However, the weakness is that he reduces his theory as the 2D analysis, which is definitely the bottom flip is the 3D analysis, but he analyzed it with the 2D analysis. Although he had tried to use the different kinds of model in the experiment, he did not account these different bottles like shape as the function of the bottle or some kind of things like that. So this is the kind of weak point of that, and other weak points are clearly summarized in this page. And also about the task fulfillment. Well, yes, did the reporter fulfill the problem requirements? So here are the following requirements related to this problem, and these requirements would be have a deeply discussion with after invite the reporter team. And here is the discussion points. I'm going to briefly summarize the discussion points that I'm going to elaborate. So here are the major key points that I would like to debate. And the first one is that how they can make the fluid as the rigid model. Since the fluid dynamics, they do not consider the angular velocity or the angular momentum or those kind of things. So I'm just curious, what kind of this angular velocity and angular momentum in their presentation means, actually, in the fluid model, real model. So the third one is that, how can the rigid model can be explained, the somersault? The first one is that if you know all the physical parameters just after the touch of the bottle to the ground, then can you determine the successful flip is going to be happened or not? There should be answer to my question. And there are 4 other discussion points, and these are all about the collision and the deformation effect and the friction, which is really important parameters related to the after landing incident. So according to their theory, they have suggested that the rebounding is not going to be encountered, so I would skip this discussion point. And how the bottle function is going to be considered, but they answered in the short question that they did not consider, so it is not really relevant question here. So this is the really important question. How the critical angle here can be existed in the constant volume. I'm going to deeply debate with this point with the dear presenter. And here are some discussion points related to the experiments. And then I'm just curious, how did they regulate the initial parameters of the launching of the bottle? And then here are the discussion points. And here are the discussion points. And the most important one is that how did they measure the angle and the all the parameters while they are flipping or not? Maybe they have used a video analysis. And I'm just curious, what kind of video analysis system they have used and how it they could elaborate on their values or not. So I'd like to gratefully invite the speaker to the podium. No, sir. So I would like to ask you some questions. So how the fluid can be assumed as the rigid body? Would you explain to me?
Well, like I said, the liquid body that I defined moves like a liquid, but it exerts force like a rigid body.
Okay, so, yes, sir.
So since the time of the collision is pretty short, I can think the collision. I can think the collision between the liquid and the solid body just like the collision between.
Okay, sir, I understand. And when you consider the fluid as the rigid body, how can you define the angular velocity and all the angular momentum inside the fluid real model that you flip the bottle? So it is there in the fluid dynamics, we cannot consider the angular velocity or the angular momentum, ladies and gentlemen. So I'm just curious how he had considered this kind of values.
In that aspect, I consider the liquid as the rigid body when considering the moment of inertia.
So it means that in the your model, you can suggest the angular velocity and angular momentum. However, in real model, you cannot suggest any physically meaningful meaning of this angular velocity and angular momentum values.
Did I ever mention about the angular velocity of the liquid?
Excuse me, sir?
Did I ever mention about the angular velocity of the liquid?
No, sir. However, you have mentioned about the rigid body model, and in the rigid body model, you have suggested that angular velocity and angular momentum. So, in your rigid body model, they are clearly stated about the angular velocity and the angular momentum. However, I'm just curious how it can be explained into the real problem, to the real fluid problem that can be explained with these kind of values.
Well, I don't see why I have to justify with this question because the angular velocity of the liquid, like you said, is pretty vague constant, right? So I didn't really take that into consideration. And simplifying the model of the rigid body situation, I just considered the angular velocity in that terms. But I just thought that the liquid moves like regular liquid.
Okay, sir. So I understand. And I'm just sorry for this of the lack of time, so I'll just move to the next point. So you did not consider the somersault actually fully in your presentation, so I will not consider this discussion point, and I'd like to move to the discussion number 4. So in the discussion point number 4, you have insisted that when you determine all the physical parameters just after the touch of the bottle and the ground, can you explain whether the flip is successful or not? So you mean that if the critical angle is formed, then can you assure that more than 90% the bottle is going to be stable, going to be reached at a stable and upright position?
Well, if I know the initial conditions, yes, I always know whether it will be success or not.
So you mean
I don't know what you mean by I know that.
So okay, this is simple question. So if the critical angle is reached when the collision, so can you assure that the after the collision, and then there will be some kind of motion?
I understand. In usual situations, yes.
Yes. Okay, thank you. And let's move on to the next 5, 6, 7, 8 discussion points. So in the 5th discussion points, I have mentioned about the collision. However, you said that you have neglected the collision. However, it is really important that the collision should be one of the major factors in this problem, because I have clearly saw in your first video that you have do you remember that the bottle flip when you have performed with your hand?
Yes.
Yes, sir. So in that video, I have clearly saw that this kind of collision is really kind of matter, because it kind of causes a little deformation, as I clearly stated at the discussion number 0.6. So at the video, at the last part of the video, I could clearly see the deformation effect of the bottle. So
do you think deformation is the major effect in the
well,
do
do you think it is minor?
Yes, I do.
Okay, if you think the minor, you're the experimenter, so I have no right to suggest that it's the major. So let's move to the next point.
And
So-
I have a comment on that. You said that I did not.
I'm sorry, sir, but since the lack of time,
Okay.
okay. So the discussion point number 7. How did you take account the friction between the bottle and this kind of things?
I didn't take that into consideration because you see, I mainly focused on the rotation, right?
Okay, sir.
Not the translation movement. So the friction, exerts on that contact point, so it exerts no torque.
Okay, sir, it's really great point, and I would like to elaborate on this question. If you see this kind of situation, so this is the critical angle 0. Do you understand? So it is unlikely this kind of movement.
Let me ask you one question. What is the critical angle that I defined?
This angle, isn't it?
What is that angle?
The angle between the bottle and the angle between the ground.
The critical angle that I mentioned was the maximum angle above which the water bottle flips over. So it's
Yes, sir. So not the critical angle. Sorry for the misconception, understanding. And I mean the angle between the bottle
the
and the
angle you are talking about.
So it just fits this way. It has.
Okay.
Okay. Do you understand?
Okay.
So if this is the ice,
Yes.
if this is the ice, this bottle can clearly make in the stable and upright position, because you said you did not consider the friction. So in your model, you can explain this kind of situation when you flip the bottle on the ice ground. When you flip it should be performed as this perfectly, same as the ground motion. However, I don't think that the ice when you flip the bottle on the ice, it doesn't.
I think we can make a successful flip over the ice.
Okay, sir. So let's move on to the next question. So, since the lack of time, how the bottle functions? So those kind of bottle parameters or those kind of things have taken into account. I have asked this at the first short question period, and then you have answered me that it is not really relevant, so you did not consider.
Well, what do you mean by bottle functions?
And bottle function is that, so this bottle and this bottle has clearly different shape. Do you agree?
Yes.
So therefore, when you set up the model, you have to take into account those kind of factors, isn't it?
Yeah, right. So I reduce it into 2D analysis, and I consider the diameter of the water bottle and the height of the water bottle.
So you have used the 2D analysis, so that's why you can neglect the bottle like kind of shape.
Yeah.
Okay, understand. So the next one is really important kind of points. And then how the critical angle can be existed in the constant value.
Well, you keep saying that I said that critical angle is constant.
You have told me. You have
misconception.
just a second, sir. You have clearly told me that when the initial parameters are all equal, then the critical angle should be the constant. When I asked you at the first part,
Critical angle is the aspect of the water bottle, not the fluid itself. You see, when you set the water bottle, the critical angle accounts for the water bottle itself, not for the fluid. I think you're saying about the maximum angle that I mentioned about. The maximum angle depends on the fluid itself, and I compared it with critical angle. Critical angle is dependent on the water bottle's aspect, just like the height.
okay, so even though the collision and all the other aspects are happening after the collision, can you consider the critical angle is constant at that kind of moment?
Yes, because it's dependent.
Well, okay. Well, I do not agree on this like kind of points because I think that these kind of factors, which is collision, those kind of factors, can affect the critical angle. So I cannot agree on your points.
I think you're too focused on the translation movement of the water bottle.
Okay, so let's move on to the
collision
experiment part.
Okay.
Okay, sir. So the first discussion point is that how did you regulate the initial parameters of the launching of the bottle?
These are the formula for the three independent variables.
Yes, sir.
So there were three independent parameters that I set on the experiment.
So how did you drop that ball?
What do you mean by
That ball.
that ball? I dropped it with a thread connected to it and I burned it, but I didn't really put that in the experiment to set a picture, so I apologize for it. So that's the method.
Okay, sir. So you only have the experiment on the ground level.
Yes, on the ground level. but
Only the ground level. So you cannot like kind of control the parameter of the height of the starting parameter, right?
I can control that parameter in the theoretical approach, but I didn't really include that in the experiment because
But you have to use the experiment to like kind of to measure the height of the initial like kind of initial bottle position, and then you have to prove your.
But you see, that's only one parameter. There are
experiment.
lots of parameters that's included in my theoretical model, so I decided to not have an experiment on that one because I have lots of other parameters to check.
Okay, sir. So. I think there are many measurements, such as coefficient of friction or those kind of restitution coefficient between the bottle and the ground. But you all neglected this kind of factors, so I will not like kind of elaborate on these questions. And the next one is related to the discussion points about the other kind of factors. So, is the data plausible or reliable? Because I could not see any error bar inside your graph. So, I'm just curious whether how many times you have did the experiment, and then how many times you have like kind of plotted the data to explain your theoretical model.
Okay, I did for this experiment and for the critical angle, I did 10 times each. And
Sir, however, if you did the 10
there
times,
is an error bar right here, and there is an error bar right here.
there is the error.
Yes, so there are.
Sorry,
I thought I was
my
small
eyes.
size.
Yeah, okay.
I thought it was small
But I
size.
think this kind of okay, sir. Okay,
Okay.
thank you. And the next one is about the why all the experimental data is smaller than the theoretical data always.
It's not always, but you see for the regular.
But your graph has